Press the bell icon and never miss the video from Flip Academy.
कंजर्वेशन ऑफ मोमेंटम. फिजिक्स में कंजर्वेशन का मतलब है नो चेंज. दैट इज अगर हम कंजर्वेशन के साथ मोमेंटम लगाएं तो उसका मतलब हो गया मोमेंटम डज नॉट चेंज और द मोमेंटम रिमेन्स कांस्टेंट ओवर टाइम. Conservation of momentum is mostly used to describe the collisions between the objects. जो important point है इसमें और note करने वाली चीज है that is the conservation of momentum is only applicable to an isolated system of objects. अब देखिए isolated system का मतलब क्या होता है. Basically it is a system that is not acted upon by any external force. मतलब ये वो सिस्टम है जहां पर कोई भी अनबैलेंस्ड फोर्सेस को हम कंसिडर नहीं करते हैं. अब इसमें आपका फ्रिक्शनल फोर्स भी आ सकता है, इसमें कोई भी एक्सटर्नल फोर्स आ सकता है. सो इन दिस थ्योरी वी आर नॉट गोइंग टू कंसिडर एनी अनबैलेंस्ड फोर्सेस. नाउ लेट्स स्टार्ट विद द थ्योरी. Suppose there are two balls A and B. The ball A has mass ma. The ball B has mass mb. Both the balls are traveling along a straight line at initial velocities ua and ub, such that the ball A collides with ball B. During collision, the ball A exerts force on the ball B. Let's say the force is Fa, while the ball B exerts force on the ball A. Let's say Fb. Now, after collision, the two balls move with final velocity Va and Vb. In order to understand it more clearly, now let's formulate it. In the case of ball A, the ball A which is moving with the initial velocity ua has the initial momentum before collision which is given by ma into ua. While the ball A moves with final velocity va after the collision. So in this case, now the final momentum becomes ma into v of A. If we calculate the change in momentum, so it becomes ma va minus ma u of A. If we take ma common, so it will become ma and in bracket it will become va minus u of A. According to second law of motion, the force is proportional to the rate of change of momentum. So we can say so that in the case of ball A, the force exerted was Fa, which is equals to the rate of change of momentum. The change of momentum, as we have already calculated in the above equation, that is ma, which is multiplied by the whole bracket, and inside the bracket there is va minus u of A. It is divided by t because we are considering the rate of change of momentum. Now let's move on to the case of ball B. In the case of ball B, it is moving with the initial velocity u of B. So the initial momentum of this ball before the collision, it will become mb multiplied by u of B. Now after collision, the ball B moves with the final velocity Vb. So in this case, the final momentum now becomes mb into Vb. If we have to calculate the change in momentum, so it is given by mb Vb minus mb ub. If we take mb common, so inside the bracket it will be vb minus ub. According to the same second law of motion, that is, the force is proportional to the rate of change of momentum, then the force exerted by the ball B is represented by Fb, which become equal to the change in momentum which can be seen from the above equation. The change in momentum, as we have already calculated, is equals to mb in bracket vb minus ub upon the time, that is t, because we are considering the rate of change of momentum. Now, during collision, we saw that the balls stick together. Here comes the Newton's third law of motion, and according to the third law of motion, for every action, there is an equal and opposite reaction. That is, if we apply this law in this particular situation, so we can say so that for every force, there is an equal and opposite force, which is Fa is equals to minus of F of B. From the two equations that we have already calculated the value of Fa and Fb, and let us substitute in this equation. So it will become Ma Va minus Ua upon T, which is equals to minus sign of Mb in bracket Vb minus Ub upon T. From both sides of the equation, the T gets cancelled out. Now open the bracket. If we open the bracket and consider the left hand side of the equation, so it will become MAVA minus MAUA, and in the RHS, it will become minus MBVB plus MBUB. On rearranging both sides, we will get MAVA plus MBVB, and on the RHS side, we will get MAUA plus MBUB. Considering the left hand side of the equation, MAVA is the final momentum of the ball A, while MBVB is the final momentum of the ball B. So if we add these two values, so it will give us the total momentum after the collision. Similarly, if we move on to the right hand side of the equation, so it gives us MAUA, which is the initial momentum of the ball A, MBUB, which is the initial momentum of the ball B. On adding the two terms, it gives us the total momentum before collision. So this is the law of conservation of momentum. Thus, from the above equation, we can say so that the total momentum of the system remains unchanged, or it remains conserved, provided no other external force acts on the system. Summarizing what we have studied till now, the first is that the conservation of momentum is used to describe the collisions between the objects. The second is that the total momentum of the system remains same, and this is called the law of conservation of momentum.